Hello, welcome to Dr. Nakamura's lecture series on Advanced Bridge Engineering. Number B-2.1. This is the T-bridge, a cable-stayed footbridge. I was engaged in its design and construction as a young bridge engineer. 1 week after it was opened, I had a telephone call from the owner of this bridge, my client. He said, "The bridge has a vibration problem. Come and fix it quickly." That was a start for this study. This lecture consists of 3 parts. Let me start part 1. The T-bridge has 2 continuous spans. The main span is 134 meters and the side span 45 meters. This is a fairly long pedestrian bridge. The tower is made of concrete, 61 meters high. The girder is a steel box girder with an orthotropic deck, 6 meters wide and 1.8 high. The bridge is long but has a narrow deck. Narrow and long is a key word of this dynamic problem. This bridge connects the boat stadium and the bus terminal. The boat race in Japan is a public gambling. There are 10 races in a day. The final race is always the day's main event. Everybody wants to see it. After the final race, all the spectators, in other words, gamblers, leave the stadium and cross the bridge to get a bus, which makes the bridge crowded like this. This video shows what happened at that time. You can't see, but people were walking on the deck. Can you see the girder is vibrating in a strange way? The stays are also moving. The vibration was small, but everybody felt it. They said, "Oh, the bridge is shaking. I get a seasick," or "Is it okay?" Something like this. The bridge owner is worried because in a special occasion like the New Year's race, the bridge is overcrowded like this. In this kind of situation, the bridge would severely vibrate and make a panic among people. I have to fix this problem, but we can't get a solution before we have to understand the mechanism of this vibration. So I attached the accelerometers to the girder and the cables. The accelerometer number 1 measures the vertical and horizontal responses of the girder. Number 2 measures the vertical direction. From number 1 and number 2, we can find the movements of the girder in the vertical, horizontal, and torsional directions. Number 3, 4, 5 measure the cable behaviors. These are the measured lateral girder displacements, which were obtained by integrating the acceleration twice. 2 data on different days were shown here. After the race is over and the people started to cross the bridge, the girder lateral displacement increases with a maximum value of 7 to 9 millimeters. This is the close-up of the girder lateral displacements at the maximum vibration. It shows a clear sinusoidal wave with an amplitude of 8 millimeters. It is converted to the power spectrum, which has a sharp peak at frequency of 0.93 Hz or period of 1.1 second. These are the mode shapes and natural frequencies calculated by FEM. As you can see, the first lateral mode has a frequency of 0.90 Hz, which corresponds to the measured frequency of 0.93 Hz. Now we get to know that the girder is vibrating in the first lateral mode. But why does this happen? What is the mechanism of this vibration? When you walk, the center of gravity of your body moves left and right, which induces the lateral force. If you are a fashion model, you walk straight, and this lateral force is small. If you are drunken, you walk left and right, and the lateral force is large. Averagely, it is about 10% of the vertical force. The pace you walk is 2 steps in 1 second, left and right foot in turn, so the period of this external force is 1 second or 1 Hz. Suppose this 1 Hz exciting force is applied to the girder, which has the natural frequency of 1 Hz. Resonance occurs and the response is amplified. I asked 30 students to sidestep on the bridge with a frequency of 0.93 Hz. Then the bridge was easily excited and the actual vibration was successfully simulated. There was one more thing to fully clarify the mechanism of this vibration. This mechanism of resonance works when there is only one pedestrian. But does it work when many people walk randomly? Suppose Mickey Mouse and Minnie Mouse walk together with the same frequency of 1 Hz. But Mickey walks left, right, left, right. On the other hand, Minnie walks right, left, right, left. What would happen? Their lateral exciting forces cancel out, producing no force. We have a problem of phase difference. Then we developed synchronization theory, which means when people walk on the moving deck, they adjust their walking to the moving deck. When Mickey and Minnie walk on the solid ground, they walk randomly. But they are walking on the vibrating deck. When the girder moves to the right, they both walk to the right and step in with their right foot. When the girder moves to the left, they both walk to the left and step in with their left foot. That's the synchronization theory. We have to validate our theory. I tackled this dynamic problem with Professor Fujino. He set the video camera at the top of the entrance building and recorded the movements of heads of the pedestrians during the girder vibration. This figure shows the head movements. It seems just one line, but there are 2 lines, head movements of 2 pedestrians. 2 people walk exactly at the same frequency and the same phase. This is another day's record, which is the same. Now the synchronization theory is confirmed. The mechanism is now clarified, but it was not our final goal. We have to suppress the vibration as a designer and contractor. First, we connected the stays with secondary cables. However, it was not effective and the girder vibration did not stop. Then we installed the tuned liquid dampers inside the box girder. Our TLD is very simple, a plastic box poured with water. Water provides additional mass and its viscosity produces damping. This is the interaction model between the structure and the TLD. The TLD is added to the 1 degree of freedom structure model. mW is the additional mass of water. There are a couple of points you have to understand when you design TLDs. Firstly, its natural frequency must be equal to that of the structure. That means TLD must be tuned. Mass ratio, the mass of TLD over that of structure, is important. When it is too small, the response does not reduce. The suppression effect increases with mass ratio, but when it is too large, it becomes expensive and not practical. Damping or energy absorption is another important point. When it is too small, the suppression effect is small. This is the test results of Fujino. X-axis is the frequency of TLD over structure, and Y-axis is the response. You can understand the response is maximum at F over Fs is 1.0, and the response with TLD is much lower than that without TLD. The advantage of TLD is cheap and easy handling compared with TMD, tuned mass damper. We installed 600 TLDs. One TLD was about 10 euro, so the total cost is about 6,000 euro. It was a very cheap solution. I have to validate the effectiveness of TLDs. We let the girder vibrate and got free vibration records before and after installation of TLDs. The vibration with TLDs decreases more quickly than that without TLDs. It shows TLD is very effective. This table shows the girder displacements measured on 2 different days. The number of spectators were almost the same on both days, so the external forces were considered almost the same. Data A is before TLDs were installed, and data B is after TLDs were installed. The girder lateral displacement of data B is about 35% of data A. This also shows TLD worked very well. However, I was worried about one thing. The inside of the box girder is very hot and humid, and would deteriorate the sealing of TLDs. It would have a durability problem. 10 years later, I anxiously checked the bridge. As I predicted, some water in TLDs evaporated and they are not working. However, I did not get a complaint from the owner. The bridge does not vibrate anymore. Can you guess why? When the bridge was constructed, we had a bubble economy. People had money to spend for boat races. In 10 years' time, economy became worsened and the number of pedestrians or gamblers significantly decreased. The exciting force diminished. We published a paper on our study in the International Journal. It did not get much attention until the same vibration occurred on this bridge, the Millennium Bridge in London. A suspension bridge with very shallow cable sag, more like a suspended slab bridge. This bridge was built commemorating the millennium year. It opened to people in June 2000, but immediately closed. This is what happened. As you can see, the girder vibrates laterally. It's much larger than the T-bridge. The bridge was strengthened to suppress the vibration. These viscous dampers were installed on the deck. Under the deck, chevron bracings, viscous dampers, and tuned mass dampers (TMD) were also installed. The vibration was successfully suppressed, and the bridge was reopened 1.5 years' time. This is the end of Part 1. Part 2 and 3 are presented on the next video.